why this attendance is so low? This is only 25 students. Adil, can you run a survey quickly with your batchmates? What is the reason for such low attendance, or do you have anything? Do you know any reason? Internet connectivity, lack of interest in the class. There could be many things. Do you know anything? Any concerns?
No, I don't think there was any specific reason.
Okay, or is it too early, 10 a.m.? I
No,
don't
sir.
think so.
It's fine.
Okay. So can you just run a survey, because 25 students, it's on not even 50%.
Yes,
I
sir. I will
think
ask.
they take the privilege of learning it from from YouTube. But yeah, it's still it's a live class, so better that they attend. All right, let's begin. So we have talked about three different modulus in the last class. You remember we talked about Young's modulus. Young's modulus. We talked about bulk modulus, and we talked about shear modulus. Right. So Young's modulus relates longitudinal strain with normal stress. Right. Bulk modulus relates pressure with volumetric strain, and shear modulus relates shear strain with your shear strain, right? That is what we had discussed. Now, let us look quickly at the relationship between these three. You can find the derivation in the Lowry's book, but I think you have also done it in your school days, so I'm not repeating it. You can find out the two extremely simple relationship. A, which is the bulk modulus, is equals to E, which is my Young's modulus, E minus 2 nu. Okay, where nu is the Poisson's ratio. Okay, and similarly, shear modulus and Young's modulus can be related as well. Shear modulus is equals to Young's modulus by 1 plus. Now, what is Poisson's ratio? Poisson's ratio can be explained in a very simple manner. For example, I had a bar, okay, which had a length of L and a breadth, width or breadth in a two dimension. It doesn't matter, of D. After I apply some stress, it gets strained, and its changed shape is something like this. So it gets elongated in one direction, and it gets reduced in the other direction. Now, say for example, the modified length is L1 and the modified width is D1. So delta L is equals to L1 minus L, and delta D is equals to D minus. So here will be D1 minus D, right? So I can simply do a mod as well, no problem. So Poisson's ratio is nothing but delta D by delta L. Okay, that is what Poisson's ratio is all about. So these two equations I want you to also take a note, which we will use in our later understanding. Now let's start talking about the elastic wave propagation. Now let's imagine I have a sphere and maybe at the center of the sphere at point P, I have created a disturbance, a mechanical disturbance. So at P, what I have created, a mechanical disturbance. Or simply, I have initiated an elastic collision. How can I do that? I take anything, something, I hit it with other, make a sound. That's an elastic collision. Okay? And then as a result, the sound wave or the acoustic wave or the elastic wave actually propagates. Right. So as a result, what would happen? The elastic wave would propagate to the body. Okay. Now, this elastic wave can broadly subdivided into two groups. One we call as the body wave, and the other one we call as the surface wave. So what is body wave? Body wave is the wave that propagates through the, that propagates through the three-dimensional body of a material. Okay, propagating through the uh, volume of the 3D object. Propagates through body of a 3D object. On the contrary, surface waves are the waves which propagates through the surface. Okay. Now, propagating through surface, what does this mean? Suppose, for example, this is my whole body. This is my whole medium. Okay. So the propagation penetration is not very deep, okay, with respect to the dimension of the whole body. With respect to this dimension, the penetration is absolutely small. That is what we call as the surface wave. Okay. So penetration is small means all the elastic collision, all the elastic collisions that happens to actually propagate the wave from point A to point B. The wave would propagate from point A to point B because, say, point A is my source. That is where I have created my disturbance. The mechanical disturbances or the elastic collisions by means of which the elastic wave would propagate from A to B would be restricted only at the very uh, tiny bit of the surface. Okay, when it will not penetrate deep. That is what we call a surface wave. And if it propagates from A to C, of course, what I would see that it would disturb everything. You know, there will be mechanical disturbance throughout the body, and that is what we call as the body wave. So this is one fundamental concept. There is another important concept that I want to talk about, and that is what we call as the difference between wait, happens difference between ray path and wavefront. So before we do that, before we discuss about ray path and wavefront, I need to know about one particular thing which we call as phase, phase of a wave. What does phase of a wave physically means? Okay. So let us think about a particular type of wave propagation, and you will see this is how P wave essentially propagates. Okay. And you know about it. So what happens in P wave propagation? We talked about it. If we have, multiple points which constitute, say, particular media, and then if P wave propagates in this direction, what I observe that individual particles actually oscillate parallel to the direction of propagation. Right? You know about this. Individual particle oscillates parallel to the direction of wave propagation. This is fundamental for P wave propagation. Right? But if we look from a mechanical standpoint, what essentially happens that before it is undisturbed, before it is disturbed, I mean in the undisturbed condition, for example, all the individual particles are kind of equidistant.
Excuse me, sir.
Yeah,
Sir, we cannot hear you properly.
yeah,
Your voice is cracking.
really? I don't know what. Now is that clear? Is it clearer? Shall I
No,
log
sir,
off
it's
and
still
log in?
cracking and your screen is responding quite late.
Even your voice is cracking, so there must be some problem in the internet. Shall I just log off and log in again? Let me just log off and log in. Okay. Screen has frozen the moment. Okay, is it better now? Okay, for some people it is clear. So that must be. Is it still clear for you, Vipul? Okay, then Saima, I think there is something wrong at your end because rest of the people can hear. So yes, I will just continue. I'm sorry for that, Saima, but I think there is some problem at your end. Can you hear me now, everyone? Just can anyone unmute and speak?
Yes, sir.
All right, so then I will just continue. Okay, so where was I? Right. So in an undisturbed condition or before the propagation of the wave actually starts, what we actually see that individual particles at an equidistant position. Now, as soon as I create a disturbance, maybe at this point, what I will observe that some particles will come close to each other, and then you know the rest is equidistant. Okay. So this is initially when I did that disturbance. Okay. This is time 1. At T2, what I will observe that these particles which were actually, so this phase, this particular phenomena, what is happening that the particles are coming together, we call it as compression, or denote it with a letter C. And then at time T2, while the wave propagates, what I observe that these particles have gone little farther than they should be. And the next batch of particles are actually close to each other. Okay, so I find a relaxation and then compression, and rest of the particles are equidistant. At time T2, okay, this circle will propagate, you know, they will come back to its original position, the one which are relaxed. The compressed one will be relaxed, and the next phase of particle would be actually compressed. They will have R, and so on and so forth. Okay. Now, of course, if I keep on disturbing, okay, if I again make a disturbance here, what would happen? Another RC circle will start. It will start with a C, then R, then C, R, C, R, C, R. So I have repetitive compressions and relaxations. So repetitive compression and relaxation. That is by which the wave would propagate. Okay. So now, for example, now I am looking at, suppose at this 3-dimension body, I have actually created my disturbance. So the wave would propagate in all directions. It will disturb all the particles in all 3 dimensions. And then say, for example, after a time T2, I'm observing this wave propagation. So I will see, suppose, for example, at this place, I have R in 3 dimension, remember, at this place, I have R. If the media is isotropic, then I will find the R to be at same distance from P in 3 dimension, right? So these will be the places for the R. And similarly, there will be places for the P as well. Now, if I join them, that will create a sphere as well. Let me use a different color. If I join them, that will create a sphere as well. And that sphere, we will call it as a wavefront. Okay? So wavefront is formally defined as is a surface where all particles are moving at the same phase. Okay, is a surface where all particles are moving at the same phase. So I can construct wavefront with R. I can also construct the wavefront with C. Okay, no problem. Both of them will be parallel to each other, right? Now it will be a perfect sphere if the media is isotropic. It will not be a perfect sphere if the media is not isotropic. That means if the wave propagates with different velocities at different directions, of course it will not be it will not be a sphere. It will be different depending on what the media is, okay, how the media is, whether it is isotropic or not. So this is what we call an wavefront. So if I just simplify the drawing, you can stop me at any point if you don't understand anything, huh? So here is my disturbance that I have created, and then I can think of an imaginary sphere around it. which we will call as wavefront. And wavefront is nothing but a surface where during the propagation of this elastic wave, all the particles are moving in the same phase. Okay. And then there is to actually make our life easier, what we can think of, if so say for example, if we look at the surface of the sphere, we can think of a plane at the surface of the sphere, and a line which is going from the and perpendicular to the surface. Yeah, that is what we call as the ray path. So, the ray path will be in all directions, in all three-dimensional directions. Why ray paths are actually thought about? Simply because it makes our life easier to understand wave propagation. Understanding wave propagation, especially when it interacts with other waves, as well as when it refracts, it becomes fairly difficult to comprehend with the concept of wavefront. Hence, we use the concept of ray path, which is a line that joins the surface. I mean, it's normal to the surface and then originates at P. Now, with that concept, let's start with the first kind of body wave. So the body waves are generally subdivided into two categories. One we call P wave or compressional wave, okay? And the other one is called S wave, shear wave. Why P wave is called compressional wave? Now you know, because it propagates in an elastic media through adjacent compression, relaxation, compression, relaxation, relaxation. Right? Now, let us imagine that this is a segment of the wavefront that I just have described to you, a curved surface. And let us say that this is the point of the intersection with the ray path. And here I am defining three mutually perpendicular axes. One along the ray path, which is X, which is one particle, which is Z, and then one mutually perpendicular to all two of them. Okay. Now, let us imagine that currently we are not essentially discussing the P wave. I mean, for the simplicity, let us say now the P wave propagation is only restricted along the direction of X. Okay, so it's not a three-dimensional propagation. Not a three-dimensional propagation. It's simply, it's not like that. It's simply like, from a point source, the P wave is propagating only along X direction. So let us say this is the direction with which P wave is propagating. Now, the component of P wave in the along the Z direction, we call it as SV, and the component along Y direction, we call it as SH. Don't be confused with the maximum horizontal stress and minimum horizontal stress. They are just the component of the P wave velocity. Okay. Now, in this particular case, of course, SV and SH is 0, but there is P. Now let us say we take a even smaller portion from this surface, which we can think of as a plane, not as a curved plane, but as a plane. Because if we take a very small surface out of it, we can think, okay, it to be a plane. Let me just clear the canvas and draw it for you because I have some derivations around it. So this is the plane, which is nothing but a very small portion of the equipotential surface. Let's say the area of the plane is AX, and this is the direction of the wave propagation. So this is the direction X. Now let us imagine a very small surface, okay, parallel to AX. Just imagine a very small surface parallel to AX, which is at a distance of dx from this surface. Okay. Now, if I want to draw it in a more simpler diagram, let's say this is the x direction. So at this point, I call it a point maybe P, and then there is another point which is Q. So P is a distance of x from any imaginary space you can imagine, from somewhere from here maybe, and then Q is at x plus dx. Now, due to the propagation of the wave, because we said that it will be, uh, you know, there will be disturbance at point P. Say it is displaced. This point P is displaced with a displacement vector of u. And this point Q is displaced with a displacement vector of u plus du. Now, if I ask you, what would be the volume of this small, body that we have just drawn? The volume of that body will be ax dx, area multiplied by thickness, and the mass of that element will be rho ax dx, if rho is the density of the medium. Okay. Now let us say the force acting on the particle P is Fx, and the force acting on the particle Q is Fx plus Tfx. So the net force on this element will be, of course, Fx dfx minus Fx, and that is nothing but dfx, which we can express as delta Fx delta x dx, right? This is one thing I want you to remember. Now, just write down if you are so let me just write down these two term here. So mass m is equals to rho ax dx, that is another thing, and the net force, let's write that as nf, net force is equals to delta fx delta x dx, and then I can erase this part. Then, if we say that the stress acting on the element is sigma xx. So what type of stress sigma xx is? Ladies and gentlemen, can you tell me whether it is normal stress or shear stress? What type of stress would it be?
The normal.
Normal stress, absolutely. So the force then will be, what would then be the force? The force would be, force per unit area is stress. So force would be sigma xx ax, and we have also calculated force, net force, from another formula. So we can write down that we know Newton's second law, P is equals to mf. What is the m I have found out? Rho delta x ax, sorry, rho dx ax, not delta, rho dx ax, that is m, and f is equals to, u is my displacement vector, so delta square u delta t square, where t is time, would be my acceleration, right? So this is my m component and this is my f component, right? That's the force. And then force also we have written as delta fx delta x dx, right? Now let us substitute fx with sigma. So delta sigma xxax. Okay, so delta sigma xx ax by delta x dx, and that I can write down as delta x ax delta x ax delta sigma xx delta x. Okay. Sorry, this is dx. Dxx delta sigma xx dx delta x. Okay. Now, what we also know from last class, that sigma xx is equals to E epsilon xx. What is E then? And what is epsilon xx? Can someone tell me what is E and what is epsilon xx? Come on. Sigma xx. Sorry?
Is epsilon Poisson ratio?
No. This is Hooke's law. We talked about in the pre-recorded lecture. E is the Young's modulus and epsilon xx is the longitudinal strain.
Okay.
Right?
Yes, sir.
Stress by strain is equals to Young's modulus. You remember that equation, Hooke's law.
Yes, sir.
So this is your normal stress and this is your longitudinal strain. And the constant is Young's modulus, right?
Yes,
so, and then, I can write down E. Now, what is epsilon xx? Epsilon xx is nothing but delta U delta x is the change in the displacement vector, right? So now if I essentially do a substitution, I can write down delta square U. Now let's just remove this. Do a substitution, I can write down delta square U by delta T square is equals to T square. I'll say what is V by delta square U delta x square, where V is nothing but root over Young's modulus by rho. Okay. So now this is the fundamental equation for wave propagation of P wave, but you have to remember that here P wave propagation is only single dimensional. P wave is only propagating along X. There is no P wave propagation in the Y and Z direction. Okay, it's only unidirectional P wave propagation. Okay? Now, if we essentially want to more generalize this particular equation, we can write down, delta square theta by delta E square is equal to alpha square delta square theta delta x square. Okay. So now what is U and what is theta? So U we have talked about is the displacement. Displacement, we talk about it is in one dimension. So what is that one dimensional displacement will be translated in terms of in three dimension. In three dimension means in one dimension. Let me try to explain that one physically. So here one dimensional displacement means displacement in one direction only, right? Now think about the displacement happening in all directions, okay? In all directions. So that would essentially compress and relax the body, right? So in other words, we call it as dilations and compressions, So when you integrate U in all directions, that comes with another term which we call dilational constant or dilations. Okay, so here theta is replaced with U. Okay, so delta square theta by delta T square is equals to alpha square delta square theta by delta x square. This is the general equation along the direction of x. Okay, general equation along the direction of x for P wave propagation. Now, of course, I can write down an equation for the delta square theta delta y square will be the three-dimensional wave propagation along y direction, and delta square theta delta z square will be propagation in the z direction. What is alpha? Alpha is nothing but k plus 4/3 mu by rho. K plus 4/3 mu by rho. Okay. Now, let's just write this term alpha in a, so alpha is equals to k plus 4/3 mu by rho. Now, for any liquid or gas, okay, for liquid or gas, what's the value of mu? What is mu, by the way? What is mu? What is k? Come on, you have to tell me. What is mu and what is k? Huh? K is the bulk modulus and mu is the shear modulus, right? So for liquid or gas, what is the value of mu? What is the shear modulus for liquid or gas? Can someone tell me? What is the value for shear modulus for liquid and gas?
0.
0, absolutely. So for liquid and gas, mu will be 0. So what I would be left with, alpha is equals to root over k by rho. Okay. Now, if I again see that equation, it's not becoming 0 then, right? So delta square theta by delta t square is equals to alpha square delta square theta delta x square. So that is not becoming 0. So what does that mean? P wave can propagate through. So the velocity doesn't become 0, right? So the P wave can propagate through liquid and gas. Okay. Now, how about S wave? Now, if we look at S wave, what happens in S wave? We know that before we talked about it, that if these are my individual particles, the particles do not propagate along the direction of the wave propagation, rather they oscillate, perpendicular to it, right? So what I observe, that with propagation I see, the some particles which propagate in the positive z, the next phase set of particles propagate in negative z, positive z, negative z. And this is time t1. In time t2, of course, this flips, so these would become, first they will be zero phase, and then they will become negative, and the ones positive, and so on and so forth, So here the phase is whether it is moving positive z or whether it is moving negative z. Okay. So here, this displacement, like there we have talked about the displacement along the direction of wave propagation that we have talked at as u, and here I am talking about displacement from the midline of the sinuous curve. So we can definitely draw a sinuous curve for S wave propagation, and this is what we call these individual distances we can call as w. That is my displacement vector, and here the equation is given. I mean, the derivation is given. You should read it from Lowry's book, pretty much included in your syllabus, but I'm not doing the derivation for you. You can find out the wave equation becomes delta square w delta t square is equals to beta square delta square w delta x square, where beta is equal to root over mu by rho. Mu is shear modulus. Now, for liquid and gas, we know that the shear modulus is 0. So, beta will be 0. And hence, the S wave cannot propagate through liquid or gas. Okay? And that is something we fundamentally established, how we can use the propagation of P wave and S wave to understand the internal structure of the Earth, if you remember. We said S wave can propagate through mantle, but it cannot propagate through outer core. Right? So hence we said, although there is convection cycle in the mantle, we do see the S wave propagation through it. So we said in a shorter time span, mantle acts as a solid. It does have some shear modulus. That is the very fundamental part that we are coming back again. Okay. In terms of surface waves, there are two types of surface waves. One we call as Rayleigh wave. What I am writing. And the other one is called Love wave. What are they? We would look into them in the next class while we talk about earthquakes. Okay, if you have any question, you are free to ask. So it is very much dependent on the biology of the material, how this wave essentially propagates. It's very much dependent on the bulk modulus, shear modulus of the material, Young's modulus. And yeah, that defines the velocity of P-wave and S-wave propagation. In one case, of course, as we have just established, that shear modulus if for liquid and gas is 0. So the P-wave can propagate because the term doesn't become 0. But S-wave cannot because beta becomes 0 when shear modulus is 0. Okay? Anything you want to ask? Any clarification you need?
Sir, this is there in the SK Ghosh book also.
No. This is from Lowry's book. You can find very nice explanation from Lowry. Only for stress and strain, because you will see it's very elementary in case of Lowry. There is a little portion given. I don't know if you have seen the book already or not. If you have gone through the book, it's very it's not written in a very nice way, but the way propagation is well described.
Okay.
Okay, so you should read it from Lowry's book. Any more clarifications that you need? Okay, if not, I'll upload a lecture tomorrow, and then we'll continue with earthquake and reflection seismology on next Wednesday. Thank you. Tomorrow is Wednesday or tomorrow is Thursday? What is tomorrow? Tomorrow is Thursday. Did we not have a lecture yesterday? No. Okay, right. Of course, we have a lecture tomorrow. I keep on. That's my own confusion, guys. I am so sorry for that. Can you, Adil? Can you just inform the classmates, because I they typically confuse Wednesday with Thursdays. Of course, there is a lecture tomorrow on Thursday, which is from morning 10. I completely get myself confused with Wednesdays and Thursdays. I don't know why. I kept on thinking that I already taught you yesterday. So yeah, that's okay. So we will have a class tomorrow, regular class from 10 a.m. Okay, and we will start with bit on earthquakes. All right, thank you guys.